Now we have the limit as x goes to 0 of absolute value of x over x. Now just like before, the denominator goes to 0, and you can easily show that the numerator goes to 0 as well, because the absolute value function looks like this, and as x goes to 0 from both sides, the y value is going towards 0. So it's an indeterminate form of type 0 over 0 again. That means we have to express the function in a different way so that it is no longer an indeterminate form of type 0 over 0. So how we're going to do this one is by splitting this limit up into two one-sided limits. So instead of evaluating the limit as x goes to 0 from both sides, we'll evaluate the limit as x goes to 0 from the left and limit from the right. And if these two limits evaluate to the same finite number, let's say L, that means this limit is also equal to L. Remember, that was a theorem from 2.2. Alright, so somehow splitting this up into two one-sided limits will allow us to express these functions in a different way that is not an indeterminate form of type 0 over 0. So to do these two limits, we're going to have to remember something about the absolute value function. We can write the absolute value function as a piecewise function without the absolute value signs. So if you remember, absolute value of x is the same as just x when x is greater than or equal to 0. In other words, the absolute value signs are not necessary when x is not negative. If x is negative though, what this does is it'll make it positive. So another way to express that without the absolute value signs is to say, well, put a negative in front of the x. And that's because negative times negative is positive. So knowing this, we can re-express the absolute value of x without the absolute value signs in these two one-sided limits. For the first one, we have the limit as x goes to 0 from the left. That means x is always negative because you're going this way. So we can re-express the absolute value of x as negative x. The denominator stays the same. Now, we have an indeterminate form of type 0 over 0 still, right? The numerator and the denominator both go to 0 as x goes to 0 from the left. However, we can now re-express this by canceling out the x's. So what we're left with is the limit as x goes to 0 from the left of negative 1. And we all know that the limit as x goes to 0 from the left of negative 1 is just negative 1. Let's do a similar thing for the second one-sided limit. Now x is going towards 0 from the right. So we're going this way. Since x is always positive there, we're going to replace the absolute value of x by x. So we get the limit as x goes to 0 from the right of x over x. Again, we have an indeterminate form of type 0 over 0, but the x's cancel out, giving you a limit as x goes to 0 from the right of 1, which is 1. Now notice that these two limits are not equal. And if you remember from 2.2, if the two one-sided limits are not equal, then the two-sided limit doesn't exist. So since these one-sided limits are not equal, that means this two-sided limit does not exist. So we'll make a conclusion down here. Since the one-sided limits are not equal, the two-sided limit does not exist. And in fact, it turns out that the graph of our function looks like this. So it goes on like this, and then it's undefined at 0, jumps over here, and keeps going on like that. So as you can see, as x goes towards 0 from the left, the y value is negative 1. As x goes towards 0 from the right, the y value is 1. They're not going towards the same value as you come from the left and the right, so the two-sided limit doesn't exist. Now, we're going to introduce to you a theorem called the squeeze theorem, sometimes also called the sandwich theorem. And this theorem can sometimes be helpful in evaluating certain limits. So here's what it says. Suppose that you have three functions, f of x, g of x, and h of x, and you have an inequality where f of x is smaller than or equal to g of x, which is in turn smaller than or equal to h of x. When x is near some number a. So here is one situation where that happens. You have an f of x, which is always smaller than or equal to g of x, which is always smaller than or equal to h of x. If it turns out that the limit as x goes to a of the smallest function and the limit as x goes to a of the largest function are equal, let's say they are equal to L, then the limit as x goes to a of the middle function is also L. And it's easy to see why that is the case by looking at this graph. Notice that the smallest function f is going towards L as x goes to a. As you keep going towards a from the left and the right, the y value is approaching L. And so is the biggest function h of x. As you keep going towards a from the left and the right, the y value is going towards L. So this is satisfied. Then what's the middle function going to do? Well, the middle function is always going to be between the smallest and the largest function. So if the smallest function and the largest function are both going towards L, then there is nowhere else for g to go. It has to also go towards L because it's always sandwiched between the smallest function and the largest function. And so we have that conclusion. As x goes to a, g goes to L as well. So that's the squeeze theorem. It turns out that the squeeze theorem also works for one-sided limits. All right, so let's see how we can use this theorem to evaluate a limit. It says to use a squeeze theorem to show that this limit is equal to 0. Now, certainly you can't do something like direct substitution. This is not a polynomial nor a rational function. And even if you did that, you're going to get 1 over 0, which is undefined. So you'll be stuck anyway. And furthermore, you can't use the limit law, which says the limit of a product is a product of the limit. And that's because you can only use the limit law if the limits on the right side both exist. This limit doesn't exist. So how you're going to use a squeeze theorem is you're going to build a function that is smaller than this one and bigger than this one. In other words, this is your middle function, g of x. And hopefully your smaller function and the bigger function both have the same limit, which will allow us to figure out the limit of the middle function here. So obviously your smaller function and the bigger function that you make up have to be functions that are easy to evaluate the limit of. All right, so let's see how we can do that. Well, remember that sine is always between minus 1 and 1. So sine 1 over x is between minus 1 and 1. So now we've bounded sine 1 over x by a smaller function and a larger function. And then you're going to multiply everything by x squared to get this in the middle. So that means the left side becomes negative x squared, the right side is x squared. And then we're going to show that the limit as x goes to 0 of this and this are the same, which will give us the limit of the middle function. All right, so let's evaluate the limit of the smallest function. That's limit as x goes to 0 of minus x squared. Well, you have a polynomial, so we can do a direct substitution to get 0. Now let's do the limit of the largest function. That's the limit as x goes to 0 of x squared. Again, direct substitution gives you 0. And they are equal. That means that we can use the squeeze theorem since this is satisfied, and we can conclude that the middle function also has a limit of 0. So by the squeeze theorem, the limit is 0. And just for your information, it turns out that this function looks like this pink graph here. Our smallest function is here. Our biggest function is here. Notice that the smallest function goes to 0 as x goes to 0. The biggest function goes to 0 as x goes to 0. So the middle one must as well. Now, before I move on, I wanted to say something about the squeeze theorem here. I often see students using the squeeze theorem wrong. So here's what I mean. Suppose that you decide to use a squeeze theorem on some function, but it turns out that these two limits are not equal to each other. So then what does a squeeze theorem say in that case? Well, it says nothing, right? So the squeeze theorem says if this is true, then this is true. If this happens to be not true, then the squeeze theorem tells you nothing. You cannot use this theorem at all. But I will often see students say, these two are not equal to each other, so this limit doesn't exist. That is not what the squeeze theorem says. You can only use a squeeze theorem if this is true. And that's true of any theorem, right? If the condition is not satisfied, then you cannot use that particular theorem. If the condition isn't satisfied, that doesn't mean that the opposite of the conclusion is true, or something like that. So just keep that in mind whenever you're using a theorem. All right, so another squeeze theorem question. So that this rather complicated looking thing goes to 0 as x goes to 0 from the right. So remember, this has to be your middle function. So you have to find a bigger function and a smaller function than this and evaluate the limits of those and hope that they're the same. We'll start with this. So again, we have a sine function which is bounded between -1 and 1. Now you want the middle to eventually look like this. So let's raise all the sides by base e to make it look like this. So that gives you e to the -1 is less than or equal to e to the sine pi over x, which is less than or equal to e to the 1. Now we'll multiply all the sides by root x to make the middle look like this. So we have root x over e is less than or equal to root x times e to the sine pi over x, which is less than or equal to root x times e. All right, so let's evaluate the limit as x goes to 0 from the right of our smallest function. This is not a polynomial or a rational function, so we won't do direct substitution. What we will do, however, though, is use a limit law, which says whenever you have a constant that's multiplied, you can bring it out. So let's bring out the 1 over e, and you have limit as x goes to 0 from the right of root x. And, well, root x, we all know what that looks like. Looks like this. And as x goes towards 0 from the right, the y value is going towards 0. So this limit is equal to 0, which means this whole thing goes to 0. Similar thing for the other limit, the limit of the biggest function. We have the limit as x goes to 0 from the right of root x times e times the limit as x goes to 0 from the right of root x. But we already figured this out from above, that it's equal to 0. So this limit also is equal to 0. Now we figured out that the smallest function goes to 0, the biggest function goes to 0. So the middle one must also go to 0 by squeeze theorem. So in other words, that limit is equal to 0. All right, so that's the end of 2.3. Homework questions from the textbook for you to do here.